optical vortices. And we proved mathematically that these optical vortices actually induce some optical forces on particles that are placed nearby, which make them rotate. And at the same time, you can also optimize them to make some particles with different sizes to behave differently. So as you can see, basically, okay, I will show you first what will be the plan of the talk. First, I will explain a little the motivation for multiphysics with examples based on my research. Then I will give you a very brief background on the equations for optical forces and start building an example on how to calculate optical forces in console. Then I will explain Brownian motion and why do we need it in our case. And then I will show how to actually calculate or predict Brownian motion using console. And if we have time, I hope that we can actually explain a little how we can also model fluid mechanics, which is also something that is quite unusual in our field of optics, but it can lead to very interesting multidisciplinary projects. So I think it's also useful to have some background on it. So what I was saying before, what did we do in our project? We designed some dielectric cube that we place over a substrate and submerge in water. And we optimize its optical response to a specific frequency point. There is no need to explain a lot about it. Simply, the only thing that you need to know is that at this point, actually, you have some special Poynting vector distribution. And this distribution leads to rotation of particles around the structure. And this can be very useful for some applications in microfluidics, where you need, for example, to mix a liquid very thoroughly, and you can actually do it with this kind of setup. So yes, basically, here you see what we can model in console. First, we calculate the electromagnetic problem, and then we can combine it with other physics in order to observe what will be the behavior of the particles near the electric structure. So we can see, we investigate the trajectories, and basically here what you see is that we combine optical forces from before and we add particle dynamics. In a second step, or third step, we can actually combine optical forces and particle dynamics plus fluid mechanics. So we observe not only the behavior of the particles, but we observe how the particles affect the fluid surrounding them. So as you see, actually, it's like building a puzzle. We start with optics, and then we add pieces step by step, which are simply adding equations and boundary conditions to the problem. So the first example, how to calculate our structure. In the second example, we will also make a simple model. We will extend the first model to also calculate the behavior of the particles surrounding the structure. And if we have time, I guess we will not build this model, but I can show you more or less how you can do it. I will show you the typical benchmark example for fluid mechanics, where you have some particle submerged in a fluid and moving due to gravity. So let's start with the simple basics so you can understand. Hello? Is there a micro on? Someone has a question? By the way, do not hesitate to ask any questions or if there is something that is not clear. I would prefer probably in the chat, but as you wish. Okay, so first I will give you the basics. I am not sure about your background with optical forces, so here I just gave the most the equations that we use, but it's not my purpose to actually explain the derivation of these equations, because the idea is to show you how to use console, not to explain the physics. But in any case, there are two ways that we can calculate the forces, the electromagnetic forces that one has in a system. So on the one hand, the most rigorous way is to calculate what we call the Maxwell stress tensor, and average it over time, and make a volume integral over a particle where we want to actually evaluate the force. Then a second option, which is actually more easy, is to consider that your particle is like a dipole, and then you can directly evaluate this expression without the need to make any volume integral. The advantage of the second approach regarding console is that for the first case, for the integration of the Maxwell stress tensor, you actually need to draw the particle, and you need to change its position in a parametric sweep every time you want to see the force at different positions of in the system. While in the second case, this directly gives the force distribution or in the whole computational domain. So it is much faster, and in fact, since it's direct analytic, a more clear, straightforward analytical expression, it is easier to understand physically. So a dipole we consider as a particle that is directly proportional to the local electric field by a proportionality constant that we call polarizability. So in general, these optical forces can be separated into two terms. One that is called gradient forces, and the second one that are scattering forces. So gradient forces in our case are not very interesting because they never lead to rotation, which is our motivation actually, to generate rotation. And these forces actually depend on the real part of this constant here. So if we find conditions so that the real part becomes zero, the only thing that are left are scattering forces, which lead to a much broader spectrum of phenomena, including rotation. So this is our purpose. Okay. So what we will model first? We will consider a silicon cylinder illuminated by a circularly polarized plane wave. And then this is the first, and then we will also introduce the analytical expressions for the optical forces.
Excuse me, please, may I interrupt you, but I did not quite understand what parts of alpha we actually need, imaginary
Yes.
or real one.
Okay, sorry, just go back. So this polarizability here, it's not my intention to actually show you how to calculate it, but the idea is that if you have this alpha with pure imaginary part, you have only this type of forces. If you have a real part, you have gradient forces. Do you know what are gradient and scattering forces?
Yes, we know.
Okay. So our idea is actually to know to only have scattering forces in our system, and this can happen. This particular effect, if you want to know the physics, it's simply because near the plasmonic resonance, there is a point for some sizes of particles where the real part becomes exactly zero and you only have imaginary part. And in the dipole approximation, this means that you only have scattering forces. So basically, if you have scattering forces, you obtain this kind of effect in your field.
Excuse me, scattering forces are dissipating energy, yeah?
Yes.
Thank you.
Yes, they are dissipating energy, but what do you mean?
No, I understood.
So when they dissipate energy, you mean that actually they cannot be associated with a specific scalar potential. Yes, and this is the reason actually why we obtain vorticity, because if your forces are can be associated with the gradient of a scalar potential, the curl of this gradient is always 0. While in the case of scattering forces, the curl is not 0, and this leads to vorticity, which is the reason why we can actually make particles rotate. Is it clear?
Yes, it is.
Okay.
Pretty much, thank you.
So as I was saying, we will take a silicon cylinder, illuminate it with circularly polarized light, and then we will calculate the optical forces, not using Maxwell's stress tensor, but with the dipole approximation. So first, let me see if I change. Do you now see console, or are you still seeing the PowerPoint?
We're still seeing the PowerPoint.
PowerPoint.
Yes, 1 second. Okay. So let's start with a, okay, maybe not with a black model. So we will do a 3D. I guess you're very familiar with console already, so I will just go very fast at the beginning. Let me just do wave optics, typical frequency domain. And then we will do a wavelength domain study. What do you usually use, frequency domain or wavelength domain?
Frequency domain is more frequent in our labs.
Okay, basically it's the same. The only thing is that you input the wavelength in vacuum, but that's it. I just want to clarify. So I will just copy paste the parameters that I have already prepared, and I will explain, probably you know already. E0 is the amplitude of our electric field. Z0 is the vacuum impedance. I0 is the incident intensity of the wave. WL is, I call it the wavelength. TPML is the thickness of the PML that we're going to make. Radius of the cylinder, height of the cylinder, radius of the physical domain, which I make equal to wavelength, but not necessarily. Refractive index of the host medium, and particle refractive index, which I just set to 4 for simplicity. So now let us start with geometry. We will build first the physical domain. And write it simply. I will make a centered on the origin, make a layer, which is the PML. And now next we will make a cylinder. It is also centered in the origin. Okay. Okay, and now we will, to make the things easier, we can make selections. And by the way, if you see some differences with respect to your version in console, it's because I am using 5.5. I guess, I hope it's not a problem. So and we will also make a final selection with all the physical domain. Okay, next, we will prepare the materials. Host refractive index. Particle refractive index. Okay, so now finally we define a perfectly matched layer, the PML, and set it to spherical. Okay, I guess until here everything is clear and there are no doubts. Okay, next thing, we will define the forces. If you want, I can actually send you a document with the optical forces so that you can have them and calculate in your own models as you'd like. I am just going to introduce them here directly, but basically they correspond to the equation that I showed previously for the dipole approximation. Do you want a text file with the parameters?
This would be great.
Okay. I guess you're not building it at the same time as me. If you're doing it, please let me know, and I will send it now. Otherwise, I will send it in the end of the lecture. Okay, so I will send it in the end of the lecture in principle. So let me just add variables, and I will call them optical forces. Well, let's just consider that the whole domain. Second. Here there are several terms that we don't need. I'm just going to delete them fast. Well, actually thinking otherwise, 1 second. Okay, so what did I define here? Fx, Fy, Fz components. And if you check one of the expressions, here you will see that you have, I've taken the real part, and alpha 0 is the polarizability. And here I have electric field times times the first component of the so okay, 1 second, maybe it's not clear directly from I don't know how to do it. So basically the expression in the forces has the gradient of the electric field times the dipole moment. So it's the gradient of the electric field, which means that it's a tensor. This is why maybe it's a little confusing. In any case, these are the expressions. I will send you the formula with like the analytical formula and the expressions later. So I defined the 3 components and alpha 0, which is the polarizability. I don't show how actually we can calculate this polarizability. There are 2 ways. The first one is using Mi coefficients. And the second one is to consider the Clausius-Mosotti relation for plasmonic particles, which is an approximation. Anyway, if you consider a gold particle of, for example, of the order of 40 nanometers, this would be the value that you would get approximately, where actually the real part of the polarizability is close to 0 because you're very close to the plasmonic resonance. So next, we have forces, we have materials, everything. We'll just define very fast also a mesh. We just set the mesh to be at least a fifth of the wavelength. And for the particle, it's the same, but just to take into consideration that the refractive index is higher. And then a free tetrahedral for the physical domain. And also a swept mesh for the PML, which is the ideal in this case. And here we consider at least 5 elements in the PML. Okay, I guess there is a small mistake here. Yes, of course. You have to consider this only for the cylinder. Okay, and if you, well, now it's clear that the distribution, you have 5 elements along the PML, and the mesh along the cylinder is more fine. So next, simply here we will just model one wavelength, calculate one wavelength, because there is I already this cylinder is already optimized, so everything is clear here. The point of this project is not to show you how to do this. It's simply to show how we can actually introduce different physics. So once the model is finished, the idea is first we will calculate the optical forces, and the next step is actually to show, okay, I guess until here everything is clear. I hope I'm not going very fast. Yes, of course. Okay, before that I went very fast. I have to define, I am going to use the scatter field formulation, and I have to define the background field. So actually, we cannot use a plane wave as given in console. We need to make it user defined because there is no circularly polarized plane wave. So I will just directly input the expression for a plane wave here, propagating along minus z. But there is really no need actually in our case. One second. So we just defined a variable k0 for the wave number. Yes, 1 second. So for those who actually use frequency domain, actually the reason why it gave this mistake is because we are using wavelength domain, and thus actually the prefix is not EMW, it's EWFD. So actually what I defined here is a left circular, well, a right circular polarized plane wave providing along minus z. So I added a phase delay of 90 degrees in front of the y component. So next step, of course, I guess everything is clear. Okay, now we'll visualize the field simply to show you. So first I made a selection, and I will add a second data set to actually show better the force distribution. So let me I made a parameterized surface. This kind of data set actually helps you to visualize better the in plane force distribution. I will show you why. Actually, you can define your own parameters. So, okay, I will show you fast. So basically, I define theta and pi, and I will make a polar a system of coordinates that will actually help to actually make your own plane. So let's say 1.5 the cylinder. So what I wrote here is basically I want a surface that makes. Yes. Any doubts?
I think it's a glitch of your microphone.
Ah, okay. So have you ever used parameterized surfaces? Is it clear what I'm doing now? Since there's silence, I assume there is something is not clear. Okay. So in principle, what I did here, I just made a polar system of coordinates and said that I want a surface that goes from 0 to 2 pi, and then the radius from 1.5 times the radius of the cylinder to r. And basically, I set the expression in a way that z is equal to 0. So basically, it will make a plane that will be at z equals 0, but it will not make the full plane. It will start at 1.5 times the radius of the cylinder. So if I plot it, this, and 1 second, because I defined the view before. Okay, so if I plot it, you see clearly here that it leaves some spacing. Why? Because the forces actually become singular very close to the cylinder, and they break, and they do not allow to visualize the whole force distribution. So now I'm going to first plot them. I will just make a selection to avoid the PML. And here, as you see, the field distribution. And now I will make also another surface in the parameterized surface that I just defined, and I will just plot the fx and fy and fz components of the force. So if I make these arrows bigger, you will actually see that we only have a z component, but this is actually a visual trick. Yes, we have only z component, but we need to realize that in a physical system, we would have a substrate below this particle, and this would compensate completely the z component. So we do not need the z component. We only need fx and fy to see what happens if you have a substrate below this particle. So if you now plot this, you will see that actually near the cylinder, you obtain a spiral force distribution. And this is actually what we wanted to obtain. Now, obviously, if you have this, you would think, okay, how to actually, so how will the particles behave in this field? It is clear that they will rotate, but what speed, what time, what will be the real trajectories when they move away from it? So this is the next step, how to actually simulate it in a real system. So now that we have all of this, let's continue. I will now switch to PowerPoint. So in the next step, actually what we want to see is what happens if we put a particle in this kind of field. What kind of forces act on them? How can we actually model the reality of the system? So we have, actually, it's just as simple as to make a force balance using Newton's second law. We have actually, if we imagine that we have this particle submerged in water, we have basically three contributions. One is obviously the optical forces that we are putting in the system with the laser. Second term here are called viscous forces, and they arise because of the liquid resistance to actually promote any movement. So when it moves, there is like a drag force that is dragging the particles around. And then, since actually your system is very small in scale, your particles can also feel the collisions of atoms of the fluid. And this actually leads to some kind of random force that we call Brownian force. While actually the average of this force is zero for some large times, this leads to some kind of random movements of your particle, as you will see in the following. Okay, so you see actually these small variations in trajectories. These are due actually to this Brownian force. So how can we actually model this in console? We can use a functionality that is called the particle tracing, which basically solves this equation for a point particle. So let us start doing this. We will do it directly in the same model. So let me first call this first step of parameters for optical forces. And then I will add a second set of parameters for particle tracing. So what do we need? We basically need temperature of the system. I will assume that the temperature is ambient temperature for simplicity. The radius of the particles that will be moving in your field. The viscosity of your fluid, in this case, is water, so it will be 8.9. But since actually we assume that the particle is like the particles are very close to some kind of plane substrate, we correct this by a factor of 1.8, which is called Faxen correction. Then this ds is just a specific value that we use to calculate the Brownian forces. I will show you later. Rho is the density of your particle. So I will assume that we have, for example, gold, which is this density. And this is simply some kind of, geometrical parameter. I will show you why we need it. So let me just minimize everything that we have until now. And now I will add from the root, I will add a second component, 2D. So here, in geometry of this second component, I will add, let's go to geometry here, it's easier. 1 second. Okay, doesn't matter. Let's just build it from. Okay, 1 second. Well, okay, I'm searching for a thing. I am not saying it, so it doesn't matter. Let's just, I will just switch. I will just make it directly. So I will add here just the same parameters as in the 3D. My idea was to make a cross section, but I'm not seeing the option. And since we are a little tight on time, I will just do it directly here. So I will just add the same radius as the one before. Well, okay, I will just build it from the geometry. I will just build 2 circles. This one will be the environment, which before we said that it had a radius r. And this one will be your cylinder. But instead of writing the cylinder, I will make it slightly bigger. I will show you with this r min that I defined in the parameters. I will explain why we need it in a second. So environment and boundary. Now, we don't need to define any materials in this case. So what we need is actually to add some physics. In this case, the particle tracing. So let's add some physics here. And search for particle tracing. Particle tracing for fluid flow. And also, we will try to finish this and add directly a study. An empty study here. And in this study, we will add a study step, which is time domain. Okay, before we go to the study, let me just directly go to particle tracing for fluid flow and start with the physics. So we have our domain, and our idea is to consider what happens here. Let's build the second Newton's law step by step. First, we will add a new drag force, which is the viscosity of the fluid. And this applies only on this domain. This is actually, let's imagine that this is where the cylinder is, although I know it's a little bigger, but I will show you why we need it. Here also, let's take out this part of the domain. In the drag force, if you see the equation, this here corresponds to viscosity times velocity, so a typical drag force. The velocities, we will assume that initially they are 0. And in dynamic viscosity, we will just write the viscosity that we defined in parameters. Also, the density corresponds to the density of your particles. So in this case, it's rho. Now, next, we will add another force, which will also apply in this domain. And for the moment, I will just assume that we already have extracted the forces. There is a final step for that. So this force is the optical force. So first we need to find a way to actually extract them from the previous simulation. But for the moment, I will just assume that we have them already as functions of x and y. Next, finally, we add a final force, which will be the Brownian force. And here, this Brownian force depends on temperature. So I will add it here. And from also the viscosity, we'll add it also from the parameters. Now, okay, everything. Yes. Okay, so now the boundary conditions for this problem are given in the walls. So there are several things for. There are several boundary conditions that one can consider. So imagine that we have a particle that starts in the middle of the domain, and at some point it will collide with the walls as long as it moves. Then these boundary conditions specifically model what happens in this case. So if they will bounce, or if they will just pass through, or if they will stick. So since we are only interested in what happens in this domain and not with other domains nearby, we will just assume that when they touch the domain, they just stay there. So I will just say that the boundary condition is freeze. Okay. Now, one thing that we need to add in the particle tracing for fluid flow is in advanced settings, we need to set the accuracy order of the wall to 1, because otherwise this makes the calculation for the Brownian force very long. So I will just leave it here. Now, finally, what happens with the optical force? How can we actually extract it from the previous domain, which is the most interesting part? So a way to do it is in the calculation, in the previous results from the previous calculation, we go to export, and we will export the data as a PDF, as a text file, and then we will import it again as an interpolation that we will use for the second physics. So we will add fx and fy to export, and a parameterized surface from the parameterized surface that I defined before. So just from one plane. And then now we'll just add here forces as a text file. And now the space dimension, we will reduce it to 2, because now we reduce the dimensionality from 3 to 1. Okay. Yes. So. Okay. It's just a simple. Simply, it's just that the file I'm trying to export is not in the correct place. So just save it here. And also, I will save the console file, because otherwise he doesn't know where I am saving. Just test. So everything's saved in my folder. Now I just exported the optical forces, and if you see it here, this is the file that we exported. You have okay, Titan R, not the best. 1 second. So instead of exporting from this parameterized surface, I will just make a cut plane and do it from the XY plane. So from here. And instead, it's better, because otherwise it's taking R and theta as parameters, and we want X and Y. So we do it from here and export the data from this cut plane. And now, if you check your file, you will see that you have X, Y, Fx, and Fy exported. Now we will actually do something a little counterintuitive. We will put it in the same model again, but as an interpolation. And here we will just use export from file and add it from here, x and fy. We say that we only have two arguments, x and y. And as arguments, the units are meters, and the function has units of newtons because it's a force. Remember that we have fx in the first position, fy in the second position in the file. So we obtain now the force distribution interpolated at any point that we wish in the 2D domain. So now we can actually, as if you go to optical force, now you see that these are already defined from the previous step. Now, in time dependent, also you need to remember that we are only solving for particle tracing. And I will just in case, I will, in the physics and variables section, I will modify the configuration to make sure that the model is only solving for the 2D domain and not for this specific effect. So I will just disable completely and make sure that we are only solving for particle tracing. I see a question, sorry. No, it's not that you have 3 dimensions in the forces, it's just that it's a 3D plot. So you have x and y on the 2D plane, and the third dimension is the force. So basically fx and fy are a function of x and y only, and x and y are on the 2D plane, and then you have the intensity in the third dimension. That's it. So now I will add a range of times. In this case, since I already did some testing, I know that actually the best is to consider a range between 0 and 800 microseconds, because the forces are actually quite intense and they make rotate things very fast. So yes, before doing anything else, actually, I will show the default solver. Of course. Before that, in the particle tracing, we also need to define the positions of the initial particles. Where are we going to place them? So here I will just add a particle release node. And then I will just select my domain. And here, actually, you have different options where you can define your particle position. So instead of mesh-based, I will consider density and 100 particles. This just means that the solver will take the domain and consider a distribution of 100 particles and will place them uniformly in this domain. And I will assume that the particles start with an initial velocity of 0. So now the mesh is clear, it's automatic, there is no real need to make it more fine. So in the solver configuration, let me just redo it. In the solver configuration, it is better to define yourself the tolerance of the solver, because otherwise it can take a long time with the Brownian motion. By the way, I will send you a tutorial for Brownian motion if you're interested, because I understand that this is very fast, and there are things that they are not very clear why we are doing them. So just in case, I will send you a tutorial. So in absolute tolerance, it is better to define it yourself, and it is recommended in the console guide that you write it to 10 to the order of 10 to the minus 6. Yes. Okay. So now let us compute and see what happens. Okay. Okay, so basically here you see different, so the default plot for particle tracings is something called particle trajectories, which basically shows the movement of the particles as a function of time. But it is not very easy to visualize it like this. It is better actually to add a tail to the particles to see how they move. So to do that, we can just go to the particle trajectories node, and in line style, you set to line. And interpolation uniform. Okay. 1 second. Okay, these things happen. 1 second. Let's see if it's probably not the best way to point out this. Not the best way to show it, but that's also a way.
Maybe you could make tail scale factor more than once.
Yes. Okay. That's it. No. It was simply a problem of I was not showing the correct time. So. Okay. So what do we see here? Initially, the particle starts at time 0, and then they gain some speed. At some point, actually, you observe that your particles start displacing themselves. It is quite. It seems that I have a mistake somewhere, because they should be rotating, and it seems like they are moving a little quite randomly. So let me see if I find the mistake. Or otherwise, I would just show you the solution that I have in a built model. My guess.
Excuse me, could you please close the add study window?
Add study. It's open still. Yes, I see. Sorry.
Picture would be bigger.
By the way, do you see my the zoom window? Because I am afraid I'm actually covering part of the console model with it.
We see.
Oh, okay. You see the console model clearly. let's see. Okay, I'm sorry. Since we are a little out of time, I will just show you what we were supposed to see in the final step. But I guess it's a very stupid mistake somewhere, so it's not a big deal. I will send you the full model so you can check it. I assume that actually it's a problem in the solver settings, because otherwise. So let me just stop sharing. So this is the same model basically. There is no big difference. And these are the results for this model. Okay. So in this case, we clearly observe that for 247, maybe it's actually the time. In any case, this is the same plot when we activate the forces. So let's assume, for example, that optical forces are 0. So we disable this model and see what occurs. So this would be equivalent to say that your forces become so your laser is disabled, let's say, and let's observe the behavior of the system when there is no there are no optical forces active. So as you see, actually, in this case, now the behavior of the particles is very random, which basically indicates that you only have Brownian motion moving the particles around the system. But when you enable your optical forces, then clearly your trajectories are totally modulated by them somehow. So we can do directly an animation, for example, for this case. So animation player or file. Sorry. And now we can observe how the behavior actually makes, how this special force distribution actually makes the particles, all this move towards some kind of optical vortex around the cylinder. So the beauty of this multiphysics is basically that you can actually combine and show the different effects that in a normal project you would never be able to. You can just guess somehow. You can just say that you have this kind of that your optical forces will modulate the trajectories of your particles. But here you can clearly observe directly how this affects the trajectories. Okay, so the final step would be to actually consider fluid mechanics in the system, but obviously we are totally out of time. So I will just consider more or less what we would do. So yes, this is the final result. And to show you, to illustrate you a little what would be the basics, let's consider a very simple model. So let's consider a particle, a sphere, that moves around a tube and starts falling from top to bottom. And in this case, instead of optical forces, you as the driving force, you would have gravity, but it's basically the same problem, just substituting with a different expressions for the force. And the beauty of this model is actually its simplicity. You can actually solve it analytically and verify it with console. So you have different assumptions that you can make here that simplify the problem and the solution in the finite element mesh. But the general approach is the following. First, you can use the particle tracing module or differential equation solving to explicitly write the force balance on the sphere. So you would have gravity and viscosity and Brownian motion times mass is equal to mass times acceleration. And you would solve in each time step this differential equation. The difference is in this case is that the drag would be, so the change in position as a function of, so first you would solve the position, and then you would take this position and this velocity for the sphere and update your mesh. So you would change your mesh as a function of time. And the same way that you are changing the mesh, for this new mesh, you would solve the fluid mechanics equation, so Navier-Stokes. Once you solve Navier-Stokes equations, you could obtain a force, a new force acting on the sphere, and re-update the differential equation, which then you would solve again for position and speed, update the mesh, solve the fluid mechanics equation, and repeat. For that, in every time step. Very useful blog actually explaining different approaches to solve this kind of problems for fluids is this one that I give here. So this would be the results actually. So on the right, you actually see what happens with the mesh. You solve the Navier-Stokes equation, you solve the force balance, and then you change your mesh accordingly. And at the same time, you can solve Navier-Stokes equations in the new mesh. So here, basically, the color plot corresponds to the change in velocity, and it shows how actually the sphere first accelerates, and at some point, its velocity becomes constant, which is something that we call terminal velocity, where your gravity is equal to your drag, basically. And then also these lines correspond to pressure. So how the pressure increases in the fluid while the particle displaces. So this would be a benchmark. And now just imagine that you, instead of writing your gravity, you can write your optical force in your differential equation by using just the same interpolation method. And then you can solve the problem the same way. So obviously for the system in consideration, the moving mesh has some complications, but essentially this is the approach. So yes, so basically this is it. We have, I hope that has been useful. I have shown you that actually you can combine many different things. For example, I didn't have time, for example, to explain you how you can actually combine the heating and electromagnetic simulation, for example, or even combine fluid mechanics, heating, and optical forces. There are many different things that you can actually try yourself to lead to very interesting problems. Yes. Okay, thank you. I'm sorry if I delayed a lot. I don't know actually how long I was supposed to speak. So someone is telling me I have extra time. Is it true?
We have 20 minutes left now.
Okay. So do you have questions?
So in one question, in your model, you've exported data to and multiphysics.
Yes.
I've heard that there is an interface built-in console for multiphysics. Can anything, considering your project, be done using this?
Okay. There are several interfaces built for multiphysics in console. The reason why I use the interpolation method is one, because it's simple. Second, because I reduce the dimensionality. And if I had solved the problem in the same 3D setup, then yes, I could have combined the two physics. But there are several issues. One, the model is more complicated and takes more time to solve. Second, let's say that there are some assumptions on the point force that are not so clear. If you want, okay, so basically the multiphysics node that you probably are speaking about is added automatically by console when you combine different physics. So I can show an example probably. Let's see. If you combine, for example, fluid mechanics and differential equations, you will have a console multiphysics node that will add this extra. And if you combine okay, so I will show you actually the last model that I just explained. Just give me 1 second and I will do it. Yes. So I'm comparing the model. So basically, this node is added automatically. Then you can have two different ways of using it. Let's assume that you have two blocks, right? You have your differential equations related to one physics problem and your differential equations related to the other physics problem. And then you can either solve the equation simultaneously or consider first the solution of one equation, introduce it in the next, and then back and forth. So depending on how you choose, your solution will be more or less, will take more or less time, will be more or less accurate. 1 second. So I will just share the screen. In this case, basically, actually, not even here you have it. But in this case, actually, for example, you have in definitions, I added a moving mesh. And this moving mesh makes, you see here an initial deformation step. And here I added a variable US, which actually corresponds to the solution of the global equations that I also defined here. see, US is a solution to the differential equation that corresponds simply to the force balance. And then you can add it in the moving mesh as a prescribed deformation of the mesh. And then with this, you solve the laminar flow for the fluid. So actually, this console multiphysics node that you're talking about appears only when your differential equations are coupled. So when you have, for example, let's imagine that you have fluid mechanics in a system where the temperature changes. So basically, your temperature changes your thermal expansion coefficient, for example, and this directly is a function of, so this you have to put it inside Navier-Stokes equations. In this case, really, you have a direct coupling, and then you can choose different strategies. So so it's not. So usually, if your physics are not extremely complicated, they do not they do not appear. Okay, some other questions. So I assume that since there are no more questions, I will finish here. I would like to give you so the solved model, and well, since if I send you the solved model, I guess there is no need to send you the parameters; they are all there. Okay, so thank you very much. Where can I actually, yes? Where can I actually send you the models? Do you have, should I send it here in the chat?
Yes, we have an email of our group now. 1 second, I'll put it through group chat.
Thanks. Is it clear how I did the interpolation though? Because I have the feeling it wasn't so obvious. Okay, I guess yes.
Ребята, проверьте, пожалуйста, я правильно написал почту?
Okay, I will send it to everyone.
Вроде как да.
So there is a group email in group chat.
I just saw it. I'm just writing the thing. Okay, I sent it directly with the solutions, so you can check. But do not hesitate to send me. So this is my mail. Do not hesitate to send me anything, any questions, or if you have doubts regarding some implementation of console that you're doing that has some multiphysics. Yes, whatever you like. Okay, can you please confirm that the mail is
Yes, we received it. Thank you.
okay? Well, I guess that's it. So thanks for listening and for the questions. And as I said, anything that any doubts, I am open to discussion.
Thank you very much.
Okay.
Yeah.
Okay.
Thank you.
I hope it was useful. I know it has been maybe too fast because I actually thought I had less time. Otherwise, I may have like taken a little more time explaining, but I wasn't sure how to. Yes. Okay. Okay. Goodbye, everyone. Have a nice Monday.
Bye.
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 Thank you. You too.
Bye.